Hello there, I am Billy, and today we are going to talk about the most high-stakes construction project in the history of the universe, building and maintaining a star. It is a story of extreme pressure, delicate balances, and the kind of heat that makes a summer day in the desert look like a walk in a freezer. By the end of this, you will understand exactly how stars shine, why they eventually stop, and how to read the cosmic map we call the Hertzsprung-Russell diagram. Let us start with the engine room, nuclear fusion. At its simplest, fusion is the process where two light atomic nuclei come together to form a single heavier nucleus. This is not just a physical change, it is a massive energy release. This happens because of something called a mass defect. When those nuclei join, the final product actually weighs slightly less than the parts you started with. That missing mass has not just vanished, it has been converted into pure energy according to Einstein's famous equation, E equals delta mc squared. Now, you might wonder why everything in the universe is not just fusing all the time. The problem is that nuclei are positively charged, and as we know from electrostatics, like charges really do not like being near each other. This is called Coulomb repulsion. To get two protons close enough for the strong nuclear force to take over and glue them together, they need to be within about 10 to the power of negative 15 meters of each other. To overcome that repulsion, you need two things: incredible temperature and incredible pressure. High temperature means the nuclei are moving with enough kinetic energy to slam into each other despite the repulsion, and high pressure or density ensures these collisions happen often enough to keep the fire burning. In stars like our Sun, the specific recipe they use is called the proton-proton chain, or the PP chain for short. It is a bit like a multi-stage dance. The net result of this dance is that four hydrogen 1 nuclei, which are just bare protons, fuse together to create one helium-4 nucleus, but it is not a clean swap. To keep the books balanced in terms of physics laws, the reaction also spits out two positrons, two electron neutrinos, and two gamma-ray photons. That gamma radiation is the light and heat that eventually makes its way out to us. So, if a star is essentially a giant ongoing explosion, why does it not just blow itself apart instantly? This brings us to the concept of hydrostatic equilibrium. Think of a star as being in a constant tug of war. On one side, you have gravity. Gravity is the ultimate pessimist. It wants to pull every single atom inward, crushing the star into a tiny point. On the other side, you have radiation pressure. This is the outward force created by all those photons from fusion hitting the stellar matter as they try to escape. When these two forces are perfectly balanced, the star is in hydrostatic equilibrium. It stays at a constant radius, stable and shining. It is a beautiful, precarious harmony that lasts for millions or billions of years. To keep track of all these stars, astronomers use the Hertzsprung-Russell diagram, or the HR diagram. Imagine a scatter plot. On the vertical y-axis, we have luminosity, which is basically the total power output of the star. This is usually on a logarithmic scale because stars vary wildly in brightness. On the horizontal x-axis, we have surface temperature. But there is a twist. In a move that confuses every student at first, the temperature scale is plotted from high to low. So the hot blue stars are on the left, and the cool red stars are on the right. Most stars, including our Sun, live on a diagonal line cutting across the diagram called the main sequence. This line runs from the top left, where the hot and luminous stars live, down to the bottom right, where the cool and dim stars hang out. When a star runs out of hydrogen in its core, it leaves this main sequence and moves into other regions, like the red giant or white dwarf areas. The path a star takes through its life is determined almost entirely by its initial mass. It all starts in a gas cloud, or nebula, which collapses into a protostar. Once fusion ignites, it joins the main sequence. Now, here is the big fork in the road. If a star has a low mass, specifically less than 8 times the mass of our Sun, it will eventually swell into a red giant, puff off its outer layers as a planetary nebula, and leave behind a hot, dense core called a white dwarf. However, if a star is a heavy hitter with a mass greater than 8 times our Sun, it takes a more dramatic path. It becomes a red supergiant and then ends its life in a spectacular explosion called a supernova. Depending on what is left over, the remaining core becomes either a neutron star or, if it is massive enough, a black hole. There is a fascinating rule for stars on the main sequence called the mass-luminosity relationship. It states that luminosity is proportional to mass raised to the power of 3.5. This tells us something counterintuitive. You might think a massive star with more fuel would live longer, but because the pressure in a massive star is so much higher, it burns through its fuel at a ferocious rate. A star with twice the mass of the Sun is not just twice as bright, it is nearly 12 times as bright. Consequently, the biggest stars are the ones that die the youngest. They are the rock stars of the universe. They live fast, shine bright, and leave a very dramatic corpse. Let us put some of this into practice with a couple of worked examples. First, let us calculate the energy released in a single pp chain cycle. We are given the mass of a proton as 1.007276 atomic mass units. The mass of a helium-4 nucleus is 4.002602 units, and a positron is 0.000549 units. We will ignore the neutrino mass for this. Step 1 is to find the total mass of the reactants. We have 4 protons, so 4 times 1.007276 gives us 4.029104 units. Step 2 is to find the total mass of the products, that is 1 helium nucleus plus 2 positrons. So 4.002602 plus 2 times 0.000549 equals 4.003700 units. Step 3 is to find the mass defect, which is the difference between them. 4.029104 minus 4.003700 gives us a mass defect of 0.025404 units. Finally, we convert that mass to energy. Using the conversion factor of 931.5 mega-electron-volts per atomic mass unit, we multiply 0.025404 by 931.5. This gives us approximately 23.7 mega-electron-volts released per cycle. That might seem small, but remember, there are trillions upon trillions of these reactions happening every second. For our second example, let us look at mass luminosity scaling. Suppose we have star A, which has a mass 3 times that of our Sun. We want to estimate its luminosity compared to the Sun. We use our relationship. Luminosity is proportional to mass to the power of 3.5. So, the ratio of the luminosity of star A to the Sun is 3 to the power of 3.5. If you put that into your calculator, you get approximately 46.8. This means star A is nearly 47 times more luminous than our Sun, despite only being 3 times as heavy. It is working much harder to stay in equilibrium. And there you have it. From the tiny dance of protons to the massive life cycles of giants, the physics of stars is a story of balance and transformation. You now know how they fuse, why they stay stable, how we map them, and why the biggest ones are the first to go. That completes our lesson on fusion and stars. For more resources, visit Billy's tutorials.